of this IUTAM symposium. And the opening speaker in the second last session is going to be Zensho Yoshida. And I will let you introduce your talk, Zensho. Welcome.
Thank you. First of all, I'd like to thank the organizers for giving me this opportunity to give you this talk. This talk will be a kind of showing some arrangements of what I have been doing for these years with collaborators, particularly Phil Morrison, Fernando Dovaro, and Robert Dewar. And the title of my talk is Singular Casimir Elements. And that is related to the phase space foliation, which already many lecturers discussed. And so, for instance, if you have a phase space, maybe it could be foliated like this. And this foliation gives a topological constraint. And so if this is the two-dimensional phase space, and if you have one constraint, you have degree of freedom just one. And so, however, the problem is of course, we do not know what is this constraint a priori. And of course, that constraint is written inside of the equation, and it is not so much obvious. And the singular Casimir means, for instance, if we try to find this foliation, that could be something like this. And this is a singularity, which I'm thinking about. And so at this singularity, the codimension, if the phase space is 2 and codimension is 2, then this is a kind of fixed point. And so then the rank changes here. So the rank change means the singularity in this lecture. And so then I'd like to find what kind of thing is this, and how these foliations are created around here. And of course, this is just 2 dimension, but I'm going to infinite dimension. So in infinite dimension, what happens, and what is such kind of singularity. So that is a problem I'm going to discuss. And of course, we do not have the complete list of such kind of the Casimir foliation. So we are just a kind of probing the infinite dimension phase space. And what kind of thing can create this kind of things, and how the phase space looks like. So that is the subject I'm going to discuss. And so the keyword is the non-canonical Hamiltonian formalism. That is typical if you invoke Eulerian variables for the fluid plasma models. And for this, we have Casimir elements. And these Casimir elements creates the phase space foliation. And of course, this Casimir is not obvious from the complex plasma fluid equation. So we must solve for this Casimir. So that is the quest for Casimir. And if one finds these Casimirs, then on the foliated phase space, we can discuss what kind of structures are created. So I'll first discuss rather simple example for this, invoking the well-known helicity, and I'm going to discuss how this bifurcation of structures are created by these Casimir elements. And then I'm going to discuss the singularity of the Poisson operator, and that gives the singular or hyperfunction Casimir. And we discuss this in the infinite dimension phase space. So these are the basic references, and I draw heavily on these things. So I start from a review of very general formulation of Hamiltonian mechanics. And very general Hamiltonian mechanics is dictated by 2 mathematical things. One is the Poisson operator, and the other is the Hamiltonian. And the Poisson operator determines the geometry of the dynamics, and the Hamiltonian represents the matter. The matter is represented by the energy, and the space-time is represented by the G structure of the geometry. And so the general Hamiltonian equation, I'd like to write in this way. And here U is some state vector living in some phase space. And H is the Hamiltonian, that is a functional of U. And by du, I mean gradient of this Hamiltonian. And J is some operator which must be skew symmetric. And so the meaning of this equation is if you have some phase space, so this is U space, U1, U2, and you have some distribution of Hamiltonian like this, and you have gradient vector, and this J is skew symmetric, so it twists the direction of this gradient vector 90 degrees. So this is the direction of motion. So low dimensional image of Hamiltonian system is something like that. And by this J, we define the Poisson bracket like this, and this angle bracket, I mean some inner product of some Hilbert space. And if this J is equivalent to this symplectic matrix, we call this Hamiltonian system is canonical. And for this canonical system, we have this the kind of Jacobi's identity, so we can formulate the real algebraic structure for this system. And by non-canonical Hamiltonian mechanics, I mean in this talk that this J operator, skew symmetric operator, may have non-trivial kernel. And by this skew symmetry, the kernel means cokernel. So that means the range of this operator may be somewhat smaller than the total phase space. So therefore, the non-canonical system is topologically constrained by this operator. And if we could integrate this kernel, integrate means if this kernel element, kernel of J, can be represented by gradient of some functional C, then we call this C a Casimir element. So therefore, if you have such kind of topological constraint drawn like this, so C determines these surfaces constraint. So therefore, the foliation is given by the level set of this functional.
In two-dimensional case, it's a stream function.
Right, in 2D. And this means, by the previous definition of Poisson bracket, this means that C commutes with every Z, every functional. So that means this C, Casimir, is the center of this Poisson algebra. And if we have such kind of Casimir functional, that means gradient of this Casimir is included in the cokernel or kernel of J, then the effective phase space is restricted on the surface. So this is the three-dimensional generalization of this two-dimensional case. And what I'm plotting here is the contour of energy norm. And in this picture, I'm just taking the energy norm just a distance from the center. Right? So this is the kind of L2 norm. And even the energy is simple. If this surface is somewhat distorted, we observe very interesting distribution of the energy on this surface. So therefore, on this effective phase space, even for a rather simple Hamiltonian, we obtain effective distribution of the energy can be extremely non-trivial. So then the question arises, what is the equilibrium point and how the stability is, and also what is the thermal equilibrium on this restricted phase space. So that is a general idea why we investigate this phase space foliation. And as I said, if we discuss the equilibrium stationary point, in a weakly coupled system means that like fluid or plasmas, this energy Hamiltonian is almost always rather simple. It's just energy norm, right? In a strongly coupled system, Hamiltonian could be somewhat strange function. So that is the origin of the structure and these kind of things. But our plasma physicists or fluid mechanics people are usually considering rather simple energy. But the phase space is not simple. So that is the origin of the structure or interesting phenomena of plasma physics or fluid mechanics. And so therefore, if this H energy is simple like quadratic form, then if you consider the equilibrium point of this one, that is just vacuum. The critical point is just the origin. So there's nothing. However, if you consider the energy on the restricted phase space on the Casimir leaf, just like a previous picture, this could be complex and non-trivial equilibrium points or bifurcation occurs. So therefore, that kind of the equilibrium point can be calculated by this so-called energy Casimir functional. If you have Casimir, then the Casimir doesn't change. If you transform energy by adding some constant multiple of Casimir, because this commutes with everything, so this doesn't change the dynamics. So therefore, the equilibrium point can be a critical point of this transformed Hamiltonian. And that is nothing but finding the minimum energy, critical energy on this Casimir constraint, and you can interpret that this is the Lagrange multiplier.
Minimum or maximum?
Minimum or maximum or any critical points. So this is the one example of such kind of bifurcated equilibrium, which I'm going to construct later. And we observe this is actually a plasma equilibrium with some twisted deformation created by the Casimir or helicity constraint. And stability also becomes somewhat interesting when we consider the Casimir leaf. If you linearize to study the stability, we can linearize the equation of motion like this. And if this U mu is the equilibrium point on the Casimir leaf, then if you perturb the state vector near this U mu and denoting by the perturbation by tildes, you basically perturb this Hamiltonian and this symplectic operator. And by the definition, this must be zero because this equilibrium point, this goes out. So therefore, the linearization is also quite simple because of this the property. And then we find that this J can be evaluated as the equilibrium point. So then this energy, this is basically the Hessian of the energy distribution. So therefore the stability, because this is skew symmetric, the stability is quite easily evaluated by evaluating the coercivity of this energy, the linearized Hamiltonian. So for these stories, I will examine in the next section of my talk, goes quite well. however, the singularity problem creates the problem rather non-trivial. And because of the nonlinearity of the system, our simplex Poisson operator is inhomogeneous function of U. It varies on the phase space. So it is no longer a constant matrix. It's the inhomogeneous thing. So the Casimir equation, the Casimir is the 0 for this one. So this is the Casimir equation we are going to solve with non-constant J. And you can look at this equation as a kind of differential equation to determine C. So our problem is to solve this differential equation to find C. And however, this U lives in the function space. So you can see that this is an infinite dimension version of the partial differential equation. Okay, so if the phase space is finite dimension, this is the partial differential equation. Okay, and as I said, the singularity is a place where rank J changes. And so like this. So the singular point is like this. And that gives the so-called Casimir deficit. The rank changes, so you miss the Casimir around there. And one very simple example of such equation is if the phase space is just one dimension. Of course, if it's a one dimension, it's difficult to consider this is a skew symmetric. But just for the example, if you consider the one-dimensional version of this equation like this, then the singular point which I'm saying is the place where z goes to 0. Right? So that is a very simple example of the singular Casimir equation. And as you know, that if this z hits 0 and has a singularity, you have this hyperfunction solution. This is the step function. So therefore, the quest for the singular Casimir is the generalization of the hyperfunction theory. And the phase space is finite dimension. It is the usual hyperfunction theory. But we are going to develop the relevant theory in the infinite dimension. So that is our regime of mathematical work. So I would say that this Casimir problem is an infinite dimensional PDE with singularity. So of course it's very, very difficult. So we cannot construct the total solution, but as I said, we can do some probe into the phase space and what kind of singularity can exist there. Okay, so let me first start with the regular Casimir foliation. And for this, everything goes rather smooth. And so here, I invoke the somewhat simplified MHD model, which is simple but still non-trivial. And the helicity is our very popular Casimir. And we find the bifurcated equilibrium points on the helicity leaves. And that means, as I said, implying that the helicity leaves, the Casimir leaf with respect to the helicity is distorted with respect to the energy norm. And of course, the energies are the quadratic form, and the helicity is also quadratic, but it has a different curvature in the phase space. So therefore, you have interesting structure there. So the MHD equations I'm going to use is incompressible version of MHD. So it's rather simple, and it looks like this. Our state vector is spanned by the fluid velocity V, incompressible fluid velocity V, and magnetic field B. And this is the Coriolis force, and this is a magnetic force. And this P sigma means a projection onto the incompressible fluid vector. And for the later discussion, I must define some notation. This L2 small sigma denotes L2 vector field that is divergence free and normal is 0. And this P sigma is the orthogonal projection from L2 to L2 sigma. So this basically kills the grad P and makes this vector to stay in the L2 sigma, incompressible vector field. So both B and B are incompressible, satisfying normal 0 boundary condition. So our phase space is this the closed set of the L2 space. So everything can be formulated in the Hilbert space. And the Hamiltonian is very simple. It's B square plus B square, kinetic energy and magnetic energy, and that is nothing but L2 norm. So the energy is simple, but the J is complex, and the Poisson operator is like this. So you see that almost all structure is in here. Energy is basically tells nothing. So it's just a quadratic form. So the Poisson operator is nothing but the basic structure of NHD. And these are two well-known Casimir elements. This is a magnetic helicity, and this is a cross helicity. And you can easily verify by formally calculating the gradient of this one and plugging in these. These will give you the kernel of this operator. And if you invoke the magnetic helicity just for the simplicity, and then if you define this transformed Hamiltonian and calculate the critical point of this the transformed Hamiltonian, you will obtain this our familiar force-free equation, force-free magnetic field equation. So we can say that this is the equilibrium point on the energy, the helicity Casimir leaf. And I'm going to solve this equation under the following setting. We find that this mu, this is like the eigenvalue problem for magnetic field, and this mu looks like the eigenvalue. And however, we have two different classes of eigenvalues for this. And one is the case when this mu belongs to the eigenvalues of so-called self-adjoint Carl operator, which I will define later. And we know that this self-adjoint Carl operator has discrete spectrum. So there are some special real numbers which determines the eigenfunction for the self-adjoint Carl operator. But we can generalize this Carl operator to a non-self-adjoint extension if omega, the domain of the plasma, is multiply corrected. So here the topology issue comes in. And then we find that this has a solution for any complex number. So to see this, we first define the self-adjoint Carl operator. And to do that, we need further decomposition of this L2 sigma. L2 sigma is a divergence-free vector field. We are considering multiply connected domain. So therefore, we have so-called harmonic field. Harmonic field means the curl V equals 0, divergence 0, and normal 0. Okay? And we know that the dimension of this harmonic field is equal to the genus of the domain. And we decompose this from L2 sigma, and the remaining part we will denote by L2 large sigma. And physically, this is the function space of divergence-free, normal-free, and flux-free. And the flux is carried by this harmonic field. And we have this theorem that this Carl operator with this operator domain. Operator domain, this Carl is defined for L2 large sigma. That means flux-free vector fields with some regularity. And also the curl of this also belongs to this. So if you define such kind of operator, we can show that this is self-adjoint. And its inverse is compact. So we have a very nice operator which has discrete point spectrum on real axis, and that is complete to span phase space. So using this, we can formulate the bifurcation problem like this. We consider omega multiply connected. And for multiply connected domain, we can define the flux for each handle. And so this flux is carried by the previous harmonic field component. And we restrict this flux as a kind of the given parameter. If you consider the perfectly conducting boundary condition, the flux must not change. So this is one external parameter to be given. And we also give a helicity, magnetic helicity. And then for given flux and for given helicity, we try to find the Beltrami equilibrium that satisfies this Beltrami equation. So this is our bifurcation problem. And changing, for instance, this helicity, we'll observe how the equilibrium point will bifurcate. And the method of solution is like this. We decompose this magnetic field into this harmonic field component and the other component belonging to L2 sigma. And as I said, this harmonic component is determined by a given flux. And then we solve this equation, separating these. And we know that this is curl-free, so we can write the previous equation like this. And you will find that this equation is inhomogeneous. So if you just write down the Beltrami equation, it looks like a homogeneous equation. However, there is hidden inhomogeneity, and that comes from this flux condition. So I made that inhomogeneous term explicit here. And to solve this, we must invert this curl minus mu to this one, to write this. So we have two branches. One branch is for the point spectrum of this self-adjoint curl operator. And if mu does not hit the special value of the point spectrum, then this has an inverse, of course, by the definition. So you can solve this equation like this. So we call this is the branch A. And however, branch B is a case when this mu hits the eigenvalue. And this is an interesting case. And of course, if this hits this, you cannot invert this. However, there is a possibility that this equation still has inhomogeneous solution, Z. And then you can solve this equation like this. So therefore, our problem is whether there exists the particular solution for this spectrum point, Z. So if it exists, this branch B bifurcates. And the bifurcation theorem can be written like this. So we find that this is a vector potential for the harmonic magnetic field. And if this eigenfunction belonging to the lambda 1, lambda j, is orthogonal to this AH, then this inhomogeneous solution exists. So this is the condition for the branch B to exist. So the branching diagram can be written like this. If you change a helicity, then the equilibrium point moves on this line, and we have branch A solution. But at a place where this the eigenvalue of the self-adjoint operator, and if this foot point exists because of this Z, then branch B can bifurcate. So you have for the same helicity leaf, you may have two solutions like this. So this is the bifurcation theorem. Okay, so therefore, for the helicity, we have relatively, the good application of the helicity, and we can consider studies the bifurcation and stability and these kind of things using the helicity Casimir. But our problem is the singularity. So I'm gradually going to a more subtle problem, and this J operator, not only the helicity, we have many other solutions if you allow the singular eigenfunctions for this one. So the next section is the study of such kind of singular eigenfunction of the kernel of this one. And because this Poisson operator in our application is a differential operator, we are solving the differential equation to determine the kernel of this one. And the kernel is the zero spectrum of this operator. And this may include singular eigenfunctions if this J spectrum is not so much simple. And the corresponding Casimir will have the singular function. And to study that, we invoke the linearized version of the previous MHD, and we linearize the Beltrami near the Beltrami equilibrium, which we investigated in the previous section. And the Hamiltonian operator reads like this, and this S is the sexual joint curl operator. It's again very simple. And you will easily find that this one changes the sign if this mu becomes greater than the first eigenvalue. So therefore, there is already the signature of the stability issue here. And the Poisson operator is written like this. And this is a differential operator with inhomogeneous coefficient. P mu is the Beltrami field. It's the function of space. So therefore, these are the inhomogeneous differential operator. And this kernel of this linearized operator has singular eigenfunctions. And that could be determined by solving the block elements like this one and this one. To make them equal to 0, we must solve for these vectors. And you can write down the equation of differential equation like this in a more explicit way with assuming some simple geometry. And for instance, if you consider the slab geometry, you can find the equation like this. And then you will find that this hyperfunction solution to this one. And we obtain a hyperfunction kernel to this one. And that I denote by this. So therefore,
in this case, your hyperfunction is just a Heaviside function.
Yeah, this is a Heaviside function. If you have the so-called resonance condition, then this degenerates, and from the degeneracy singular point, you can obtain some solution. And using that, we obtain using this singular Casimirs determined by such kind of step function like the kernel. Then we can calculate similarly the equilibrium structure like this. And then you will obtain somewhat singular equilibrium solution. And that is the so-called the tearing mode in plasma physics. So tearing mode can be said that it's the kind of a singular equilibrium solution, stationary solution, living on a Casimir leaf determined by such a singular eigenfunction. So then, finally, I'm going to discuss the infinite dimension singularity, infinite dimension version of this, and show when this kind of singular point exists. So we are solving this Casimir equation in infinite dimension, U. And if rank of this changes, that is the singularity for this differential equation in some sense. And we can generate some singular Casimir element, singular solution of this one by generalizing the notion of this derivative. Of course, to consider such kind of a hyper function like the solution to be a solution to some differential equation, we must generalize the notion of this derivative. So for that, we invoke 2D MHD, somewhat simplify the original 3D, and to do that, we invoke that familiar Krevich parameterization for velocity and magnetic field, and this phi is a stream function, and C is the magnetic flux function. And we write the Hamiltonian in terms of omega. Omega is the vorticity, and that's the Laplacian of the stream function, and magnetic flux function. A little bit strange choice, but you can make other formulation, but I think this is most popular way of choosing variables in plasma. Maybe Hirota-kun used the same kind of representation in his talk. And then the energy reads like this. And here, this is a Laplacian, and K denotes the inverse operator of the Laplacian. And the Poisson operator, if you invoke this, these are the state variables, then the Poisson operator looks like this. And this small bracket means the usual Poisson bracket in the coordinate space, like this. So this is our Poisson operator. And again, it's inhomogeneous with respect to the state vector. So to investigate the singular solution, we must be somewhat more serious about the functional definition of these kind of things. And we can no longer live in the sieve of the regular functions. We must consider more irregular kind of functions. So our phase space we take like this. Omega lives in H minus 1 and C lives in H1. And Poisson operator can be defined in some weak sense by assuming this omega lives in C0 and C10. Then we can define that this J is a map from this function to this function space. And the domain of the generator is rather restricted, but it's considerably wider than conventionally. Of course, the sieve of the regular function is too small to discuss these kind of things, fluid mechanics. But we know that this is large enough to host the regular solutions, strong solutions.
Excuse me. I noticed this several slides ago. For example, your U. Are you sure that it belongs in the tensor product? I think it's the direct product, isn't it? Because it has two components. I don't think it's the tensor product. It's the direct product of the two.
Yeah, maybe.
Yeah, tensor product has a different meaning in mathematics. It's not. That's not tensor. It's just a simple cross.
But if you use direct product, this 0 plus 0 this. So in some sense, I wrote it's a kind of a.
No, it's not.
Okay.
It's not the direct sum. It's direct product.
Yeah. Okay.
It's not tensor.
Yeah. I'm not meaning this is tensor.
But that's the symbol for tensor product. So
but
you should be a little careful in the choice of notation.
Okay. Okay. So then the kernel, we are looking for the kernel of this one, and the obvious one is like this. But we find a big rank change if C is constant. I mean that the plateau of this one, and that means that this is unmagnetized case. So if this is the case, this vanishes, and then we have new Casimir, and that is the entropy. And moreover, the plateau can exist also for this one, and then this becomes 0. So this is the singularity like this. So therefore, we have this kind of generalization. So we know that now we find out that what is the singularity in the function space, and that is the plateau of this C. So this is a picture. If you have some plateau or in a region for this C like this, then in the plateau, you can have this function generating Casimir can have a step like this. So in addition to this Lipschitz continuous part, you can add this the singular part, and that makes this singular Casimir. So this one, this F, is kinked at this plateau. So therefore, this is the integral of this step function. So you have a kink. And for the that kind of kinked functional, we can define this functional derivative in some sense, quadratic derivative, and then we can define this. So this is the solution. So as a concluding remark, first we discuss the regular Casimir elements and the helicity, and using that we observe that the bifurcation of the regular equilibrium point. And then we discuss the singularity of J, and then singular eigenfunctions created singular equilibrium points, and that is a Tearing mode. And we further found the singularity of this operator, and that was a kind of the plateau of this, and that will create the singular Casimir elements. And finally, I'd like to end this talk with somewhat mysterious comment on the hierarchical structure of the Casimir elements. So maybe you notice that we solve for the singularity kernel for this J operator. This is a PDE. So the singularity for this one means that it's the singular point for this is the principal symbol of this one. So this is a point. So if you have a singularity for the PDE operator, you have a singular point, and that generates a singular eigenfunctions. And for the singular Casimir has the one order higher meaning, and this is no longer the point. It's the cokernel of J operator. And so we find that this singularity is nothing but it's a kind of D module of the differential operator. And so that is this thing. So this is kind of such kind of things in the function space. Okay. So, thank you.
Thank you, Zensho. Any questions? Yes.
Can you give us a physical example of the bifurcation of a singular equilibrium?
Singular equilibrium of
for
this
example.
one.
Yes.
Yeah, I just ran very fastly. Yeah, so this is a singular eigenfunction determined by the singularity.
So what's the physics behind? What's the physical example?
Physical example is the so-called Tearing mode. And if you have the resonance, then at the resonance you may have a singular current. That is a kind of a delta function like current, which corresponds to this kink here. And the Tearing mode can be interpreted as a kind of a singular equilibrium solution living on this singular. I didn't bring the picture of this one, but it's a kind of Tearing means the island. Inside the plasma,
Yes.
there develops island structure, and island is associated with singular current.
Yes.
And
so that C tilde is the current density or something?
No, this is a flux function,
It's a flux.
and the current density is the double prime of this one.
I see. I see.
So that becomes the thing.
That becomes.
Thank you very much. Keith Moffat.
Yeah, well, I just like to say I found this presentation very beautiful. I'd like to draw attention to the fact that back in the 1990s, I published a short series of papers with Vladimirov, which was concerned with the relaxation to equilibrium on what you call the Casimir foliation when in the ideal MHD, when you have the two Casimir types, that's to say magnetic helicity and cross helicity. And so it was a rather artificial relaxation procedure that drives you to equilibria, stable equilibria on these leaves.
Right. Yeah, no, thank you for the important comment. As I draw this picture, we have, if you have bifurcated equilibrium point on the helicity Casimir, then that the singular Casimirs associated with the tearing mode is basically foliating between this. So in ideal mechanics, you cannot go from here to here. However, because of that singularity, any kind of singular perturbation can destroy. So therefore, physically, people believe that at this point, we can show that this is the unstable one, so it goes to here, breaking that the leaves associated with these singular Casimirs.
One quick question,
Yeah,
and then
I was just curious to moving in a different directions, i.e., possibly extending to, or already done maybe, from closed curves to open curves or open field lines. Would you consider, so you gave a number of examples where you assumed that divergence-less conditions.
Right.
How crucial would be to drop that assumption? Because for Casimir, for helicity, you would consider then the asymptotic case of helicity, I think, would be.
You mean that the divergence free for the
velocity
field? Yeah, that we can easily
drop that.
Yeah, it is not necessary.
Not necessary.
Yeah, just for this present presentation, I just dropped. But you can include the compressibility for the fluid, and then your state vector must include the density.
But you could also go in the direction of open field lines.
Magnetic field lines, or
You would go towards the Arnold approach of helicity, the asymptotic linking numbers. That would still.
Maybe I'm not understanding your question. Maybe later.
yeah, shall we continue this afterwards? And thank you very much again, Zensho.